124 light-years from Earth. A planet called K2-18b orbits quietly around a dim red star. Recent observations suggest this distant world may be entirely covered by a vast, deep ocean beneath a thick hydrogen atmosphere. Astronomers studying its atmosphere have detected signs of water vapor, making this planet one of the most compelling ocean world candidates known so far. Unlike rocky planets with continents and shorelines, this world may be shaped entirely by water, pressure, and chemistry, unlike anything in our solar system. This is the Drowsy Astronaut, where we take our time exploring the universe without rushing through it. Whether you're listening out of curiosity, to unwind, or simply letting this play quietly in the background, you're welcome to stay as long as you'd like. If you feel like sharing where you're listening from tonight, the comments are always open, and if this helps you relax, subscribing is always appreciated. The story of this ocean world begins in the year 2015, during an extended mission of the Kepler Space Telescope. Kepler had already discovered thousands of planets beyond our solar system by watching stars for tiny, repeated dips in brightness. When something passes in front of a star from our perspective, it blocks a small fraction of the starlight, and that dimming can be measured. This simple but powerful technique revealed a universe far more crowded with planets than anyone had imagined just a few decades earlier. During what astronomers called the K2 mission, the telescope turned its attention to a faint red star in the constellation Leo. This star, now known as K2-18, is much smaller and cooler than our Sun, glowing with a dim reddish light. Kepler noticed that its brightness dipped slightly every 33 days, a rhythm that suggested something was orbiting it, passing between the star and Earth. That something turned out to be a planet roughly 8.5 times the mass of Earth, sitting in a very interesting location. The planet orbited within what scientists call the habitable zone, the region around a star where temperatures might allow liquid water. Too close to a star, and water boils away into steam, leaving a scorched and barren surface behind forever. Too far, and water freezes solid, locking a world in permanent ice with little hope for the chemistry of life. But in that middle region, conditions might be just right for water to exist in its liquid form on a planet's surface. Finding a planet in the habitable zone is exciting, but it doesn't guarantee anything about what that world is actually like. Many planets orbit in this region without having oceans, atmospheres, or any of the conditions we associate with life. The habitable zone is simply a starting point, a reason to look more closely, a hint that something interesting might be happening. And so astronomers began to pay very close attention to this newly discovered world orbiting its dim red star. What made K2-18b particularly intriguing was its size, falling somewhere between Earth and the ice giants of our solar system. We don't have any planets like this orbiting our own sun, so we had no direct comparison to help us understand it. Is it a large rocky world with a thick atmosphere, or a smaller version of Neptune with deep layers of gas and ice? The answer would determine whether this planet could have a surface at all, let alone one covered in water. In the years following its discovery, astronomers gathered more information about the planet using ground-based telescopes and orbital observatories. They refined their measurements of its size and mass, trying to calculate its density and make educated guesses about its composition. A dense planet would suggest rock and metal, while a less dense planet might indicate lighter materials, perhaps water and ice. The numbers they found suggested something fascinating. this world might be less dense than a purely rocky planet should be. One possibility that emerged was that K2-18b could be what scientists call a water world, a planet with a significant fraction of its mass made up of water. Not just a little water, like Earth with its relatively thin oceans, but water making up a substantial portion of the entire planet. If true, this would mean oceans deeper than anything we could imagine, possibly hundreds of kilometers deep, pressing down with immense weight. But density measurements alone couldn't tell the whole story, and astronomers knew they needed to study the planet's atmosphere directly. The challenge was that K2-18b is very far away, and its star is quite dim, making detailed observations difficult. Still, the planet's position in the habitable zone and its unusual size made it a priority target for the most powerful telescopes available. The technique used to study exoplanet atmospheres is called transit spectroscopy, and it works by analyzing starlight that passes through a planet's atmosphere. When the planet crosses in front of its star, a tiny fraction of the starlight filters through the thin shell of atmosphere around the planet's edge. Different molecules in that atmosphere absorb different wavelengths of light, leaving a characteristic fingerprint that astronomers can detect and analyze. This is easier said than done, especially for a planet orbiting a dim star more than 100 light-years away from us. The signal is incredibly faint, buried in noise and requiring careful statistical analysis to extract meaningful information from the data. But by the late 2010s, telescope technology had advanced enough to make this kind of observation possible for certain well-positioned planets. K2-18b was one of those planets, and in 2019, two independent teams of astronomers announced a remarkable finding. They had detected water vapor in the planet's atmosphere, the first time water had been found in the atmosphere of a potentially habitable world. The discovery made headlines around the world and sparked intense interest in this distant ocean world candidate. The presence of water vapor didn't prove that liquid oceans existed on the surface, but it was an important piece of evidence. It showed that water was present in the planet's atmosphere in significant quantities, and that the conditions there were at least compatible with water. Combined with the planet's position in the habitable zone, this finding made K2-18b one of the most intriguing worlds known beyond our solar system. Scientists were careful to note that many questions remained unanswered, and that much more observation would be needed to understand the planet. Was the water vapor part of a thick, crushing atmosphere with no real surface below, or did it sit above a vast planetary ocean? What other molecules might be present, and what could they tell us about conditions on this distant world far from our sun? The discovery of water vapor was just the beginning of the story, a tantalizing hint of what might be waiting to be found. In the years that followed, astronomers would turn even more powerful instruments towards this distant world, revealing new details that would make it even more fascinating. The picture that emerged would suggest something remarkable. A planet genuinely unlike anything in our own solar system. For now, the newly discovered world continued its steady orbit around its dim red star, completing 1 year every 33 days. Whatever secrets it held remained locked away across 124 light-years of empty space, waiting for our technology to catch up. But the first pieces of the puzzle had fallen into place, and the scientific community was paying very close attention. The discovery of K2-18b and the detection of water in its atmosphere marked a turning point in exoplanet science. It showed that we could not only find distant worlds, but actually begin to understand what they might be like. The techniques that revealed water vapor would soon be applied with even greater precision, using telescopes not yet launched when the planet was discovered. This ocean world candidate became a symbol of how far our understanding of distant planets had come in just a few decades. From simply detecting the existence of exoplanets to actually analyzing their atmospheric chemistry, each step brought us closer to answering profound questions. What kinds of worlds exist beyond our solar system? And could any of them harbor conditions suitable for life as we understand it? The answers would come slowly, one observation at a time, building a picture of a world far beyond our reach. And this is the journey we'll continue together, exploring everything we've learned about this remarkable planet orbiting its dim red star. There is much more to discover in the chapters ahead, including findings that would surprise even the astronomers who first detected this world. The red star K2-18 continues to glow quietly in the constellation Leo, and its ocean world candidate continues its endless orbit. What we've learned about it so far is just the beginning of a much larger and more fascinating story unfolding across the cosmos. In the next part, we'll turn our attention to the star itself, learning about red dwarfs and what life might be like under their dim, steady light. Every planet exists in relationship with its star, shaped by the light and energy that falls upon it across millions of years. To understand K2-18b, we must first understand the star it orbits, a small red dwarf glowing faintly in the constellation Leo. This star is the reason the planet exists at all, and its properties determine much about what conditions might be like on that distant world. Red dwarfs are the most common type of star in our galaxy, making up roughly 70% of all the stars that exist. Despite their abundance, they are difficult to see with the naked eye, because they are so much dimmer than stars like our Sun. The star K2-18 is no exception, shining with less than 1% of the Sun's brightness, despite being a genuine star in its own right. If you were to look up at the night sky from Earth, you would never notice it without a telescope to help you. The term red dwarf describes stars that are smaller, cooler, and less massive than our Sun, typically ranging from about 8 to 50% of the Sun's mass. These stars burn their hydrogen fuel much more slowly than larger stars, which means they can shine for extraordinarily long periods of time. While our Sun will exhaust its fuel in roughly 10 billion years, a red dwarf like K2-18 could continue burning for trillions of years. This incredible longevity means that planets orbiting red dwarfs have vast stretches of time for interesting things to happen. The color of a star tells us about its surface temperature, with blue and white stars being the hottest and red stars being the coolest. K2-18 has a surface temperature of roughly 3,500 degrees Celsius, compared to our Sun's 5,500 degrees Celsius at its surface. This cooler temperature gives the star its characteristic reddish glow, a warm and muted light, very different from the bright yellow-white of our Sun. Any planet orbiting this star would be bathed in light shifted toward the orange and red end of the spectrum. Because red dwarfs produce less energy than larger stars, their habitable zones are located much closer to the star itself. A planet would need to orbit nearby to receive enough warmth for liquid water to potentially exist on its surface. This is exactly the situation we find with K2-18b, which orbits its star at a distance of roughly 21 million kilometers. By comparison, Earth orbits the Sun at an average distance of about 150 million kilometers, roughly 7 times farther out. This close orbit means that a year on K2-18b lasts only about 33 Earth days, the time it takes for one complete journey around its star. Imagine a world where seasons, if they exist at all, cycle through more than 11 times in a single Earth year. The concept of time would feel very different on such a world, with each orbit completed before a full Earth month has passed. The close orbit also means that the planet likely experiences significant gravitational effects from its star, possibly including a phenomenon called tidal locking. When a planet is tidally locked, one side always faces the star while the other side faces away into eternal darkness. Our own moon is tidally locked to Earth, which is why we always see the same face of the moon from our planet's surface. If K2-18b is tidally locked, it would have a permanent day side receiving constant light and a permanent night side in endless darkness. Between these two extremes would be a twilight zone, a ring around the planet where the star hangs forever near the horizon. This arrangement creates fascinating possibilities for atmospheric circulation, ocean currents, and temperature gradients across the planetary surface below. The star K2-18 is located approximately 124 light-years from Earth, placing it in our cosmic neighborhood, but still impossibly far by human standards. Light itself, traveling at 300,000 kilometers per second, takes 124 years to make the journey from there to here. When we observe this star today, we are seeing light that left its surface well over a century ago, before anyone alive today was born. Despite this vast distance, modern telescopes can gather enough light from K2-18 to study both the star and its planet in remarkable detail. The techniques of spectroscopy allow astronomers to break starlight into its component wavelengths, revealing information about temperature, composition, and even motion. By studying how the star wobbles slightly due to the gravitational pull of its planet, astronomers can measure the planet's mass with considerable precision. Red dwarf stars have some characteristics that make their planets particularly interesting targets in the search for habitable worlds. Their small size means that planets passing in front of them block a larger fraction of their light, making transits easier to detect. Their dim light means that habitable zone planets orbit close enough for their transits to occur frequently, giving astronomers more opportunities to observe them. However, red dwarfs also present challenges for planetary habitability that scientists continue to study and debate among themselves. Young red dwarfs tend to be more active than our Sun, producing powerful flares that could strip away planetary atmospheres over time. These stellar tantrums can bathe nearby planets in harmful radiation, potentially sterilizing surfaces and making it difficult for life to gain a foothold. The good news is that red dwarfs tend to calm down as they age, becoming more stable and predictable over billions of years. K2-18 is estimated to be several billion years old, meaning it has likely settled into a quieter phase of its stellar life. Any planet orbiting it today would experience a much calmer radiation environment than it might have faced in the distant past. Another consideration is the type of light that red dwarfs produce, which is shifted toward longer wavelengths compared to sunlight. On Earth, photosynthesis evolved to use the visible light that our Sun produces most abundantly, particularly in the red and blue portions of the spectrum. Plants on a world orbiting a red dwarf would receive different light, potentially requiring different biological solutions if photosynthesis exists there at all. Scientists have speculated about what plant life might look like on a world bathed in the reddish light of a red dwarf star. Some have suggested that plants might appear black to our eyes, absorbing all available wavelengths to maximize energy capture in the dim environment. Others have proposed that life might use different chemical pathways entirely, adapted to the specific light conditions of its home star. The star K2-18 will continue shining for an almost incomprehensible length of time, far outlasting our own sun by trillions of years. Any life that might exist on its ocean world would have vast stretches of time to evolve and develop, limited perhaps only by the eventual heat death of the universe itself. This is one of the most remarkable things about red dwarf systems. They offer stability on timescales that dwarf anything in our own solar system. When we look at this dim red star in the constellation Leo, we are looking at a type of sun that is far more common than our own. Most stars in the galaxy are red dwarfs, which means most planets in the galaxy orbit stars like K2-18 rather than stars like our Sun. Understanding these systems is essential if we want to understand the broader landscape of worlds that exist throughout the Milky Way galaxy. The relationship between the planet and its star is intimate and defining, shaping everything from surface temperatures to the length of days. In the case of K2-18b, this relationship creates conditions that astronomers find genuinely intriguing and worthy of continued study. The dim light of a red dwarf may seem inhospitable to us, but the universe has proven endlessly creative in finding ways to make worlds habitable. As we continue our exploration of this ocean world, we carry with us an understanding of the star that illuminates it with its steady, ancient light. Every feature of the planet, from its possible oceans to its thick atmosphere, exists in the context of this relationship with its parent star. Next, we'll explore the groundbreaking discovery of water vapor in the planet's atmosphere, and what that finding meant for our understanding of this distant world. In 2019, astronomers announced a discovery that captured the attention of scientists and the public alike around the world. For the first time, water vapor had been detected in the atmosphere of a planet orbiting within the habitable zone of its star. The planet was K2-18b, and the finding suggested that this distant world might be far more interesting than anyone had dared to hope. The detection was made using a technique called transit spectroscopy, which takes advantage of those moments when a planet passes in front of its star. During a transit, a small amount of starlight passes through the thin shell of atmosphere surrounding the planet's silhouette against the star. Different molecules in that atmosphere absorb light at specific wavelengths, leaving characteristic signatures that can be detected and analyzed by sensitive instruments. The telescope used for this groundbreaking observation was the Hubble Space Telescope, which has been orbiting Earth and studying the universe since 1990. Hubble observed multiple transits of K2-18b over a period of years, carefully measuring the starlight that filtered through the planet's atmosphere. By combining data from many transits, astronomers could build up enough signal to detect the faint absorption features of water molecules. Water absorbs light strongly at certain infrared wavelengths, creating a distinctive pattern that is relatively easy to identify once you have enough data. When astronomers analyzed the Hubble observations, they found clear evidence of this water signature in the planet's atmosphere. The signal was strong enough that two independent research teams, working separately, both reached the same conclusion about the presence of water vapor. This discovery was significant for several reasons that went beyond simply detecting another molecule in an exoplanet atmosphere. Water is essential for life as we know it, and finding it in the atmosphere of a habitable zone planet felt like an important step forward. It suggested that the conditions on K2-18b might be more Earth-like than other exoplanets studied previously with similar techniques. Of course, the presence of water vapor in an atmosphere doesn't necessarily mean that liquid oceans exist on the surface below. Venus has water vapor in its atmosphere, but its surface is a hellish landscape of crushing pressure and temperatures hot enough to melt lead. The water vapor detection was a promising sign, but astronomers knew that much more information would be needed to understand this world. The amount of water vapor detected in K2-18b's atmosphere was substantial, suggesting that water is a major component of the atmospheric chemistry. Models suggested that water vapor could make up anywhere from a fraction of a percent to as much as 50% of the detectable atmosphere. This wide range reflected the uncertainties in the data and the difficulty of interpreting observations from more than 100 light-years away. What astronomers really wanted to know was whether the water vapor was part of a deep, crushing atmosphere with no real surface, or whether it sat above something more interesting. A planet could have water vapor in its atmosphere, while still being a Neptune-like world with no solid or liquid surface at all. Alternatively, it could be a true water world, with oceans beneath a relatively thin atmospheric layer above the surface. The Hubble observations couldn't definitively distinguish between these possibilities, but they pointed toward more favorable interpretations for some scientists. The data seemed more consistent with a planet that had an atmosphere extending above a surface, rather than a thick gaseous envelope with no bottom. This interpretation was tentative and would require more observations to confirm, but it kept the ocean world possibility alive. In the years following the water vapor discovery, K2-18b became one of the most studied exoplanets in the scientific literature. Researchers built computer models trying to understand what conditions on the planet might be like, exploring different scenarios for its atmosphere and surface. Some models suggested a world with a hydrogen-rich atmosphere above a water ocean, while others proposed different compositions and structures. The hydrogen in the atmosphere was particularly interesting because it could help keep the planet warm despite the relatively dim light from its star. Hydrogen is an efficient greenhouse gas, trapping heat and raising surface temperatures above what they would otherwise be in such a location. A thick hydrogen atmosphere could make the difference between a frozen world and one with liquid water on its surface. This combination of water vapor and possible hydrogen created a picture of a planet quite unlike anything in our own solar system. Earth has a nitrogen-oxygen atmosphere with only trace amounts of water vapor and almost no free hydrogen at all in our air. K2-18b seemed to represent a different kind of habitable world. One that might be common in the galaxy, even if it has no analogue among the planets we know best. The discovery also raised questions about how such a planet might form and evolve over billions of years of cosmic history. Did it form farther out from its star and migrate inward, bringing water, ice that later melted as it approached the habitable zone? Or did it form roughly where it is now, accumulating water from the disk of gas and dust that surrounded the young star? Understanding the history of this planet would help scientists understand how common such worlds might be throughout the galaxy and beyond. If water worlds form easily and frequently, then the galaxy might be teeming with oceanic planets orbiting red dwarf stars everywhere we look. If they require special circumstances, then K2-18b might be a rare and precious example of an unusual type of world. The water vapor detection set the stage for even more ambitious observations that would come in the following years with new technology. Astronomers knew that a more powerful telescope could reveal additional molecules in the atmosphere, building a more complete picture of this fascinating world. They would not have to wait long, as a new observatory was already being prepared for launch that would transform our understanding of exoplanet atmospheres. For now, the scientific community celebrated a genuine milestone in the study of worlds beyond our solar system and what they might contain. Water, the molecule most associated with life and habitability in our minds, had been found in the skies of a distant planet. Whatever K2-18b turned out to be, It had earned its place as one of the most intriguing worlds known to science. The constellation Leo continued to host this remarkable system, invisible to the naked eye, but now famous among astronomers worldwide for its discoveries. The dim red star and its ocean world candidate had become a priority target for every major telescope and observing program focused on exoplanets. The next chapter in this story would be written by the most powerful space telescope ever built, revealing secrets that Hubble could only hint at. In the next part, we'll explore what happened when the James Webb Space Telescope turned its unprecedented instruments toward this distant world. On December 25th, 2021, a rocket lifted off from French Guiana, carrying humanity's most ambitious space telescope ever built. The James Webb Space Telescope represented decades of work by thousands of scientists and engineers from around the world working together. Its mission was to peer deeper into the universe than ever before, and to study the atmospheres of distant planets in unprecedented detail. After a nail-biting deployment sequence that unfolded over several weeks, the telescope reached its final destination about 1.5 million kilometers from Earth. There, at a gravitationally stable point called L2, it began cooling down to the frigid temperatures needed for its infrared instruments to function properly. By the summer of 2022, James Webb was ready to begin its scientific mission, and exoplanet researchers were eager to use it. K2-18b was high on the list of priority targets for the new telescope's exoplanet observation programs from the very beginning. The water vapor detection by Hubble had tantalized scientists, but Webb's instruments could see the planet's atmosphere in far greater detail than before. With its larger mirror and more sensitive detectors, Webb could detect molecules that Hubble had no hope of seeing clearly. In 2023, the James Webb Space Telescope observed K2-18b during 2 separate transits as it passed in front of its dim red star. The telescope's instruments captured the faint light filtering through the planet's atmosphere, recording information across a wide range of infrared wavelengths simultaneously. When astronomers analyzed this data, they found a wealth of new information that significantly advanced our understanding of this distant world. The results confirmed the presence of water vapor that Hubble had detected, but they also revealed much more about the atmospheric composition. Webb detected clear signatures of carbon dioxide and methane in the planet's atmosphere, 2 molecules with important implications for surface conditions below. The presence of these carbon-bearing molecules painted a picture of a chemically active atmosphere, quite different from the thin, nitrogen-rich air of Earth. Carbon dioxide is familiar to us as a greenhouse gas, but its presence in K2-18b's atmosphere suggested something interesting about the conditions there. On Earth, carbon dioxide cycles between the atmosphere, oceans, and rocks through complex geological and biological processes over long timescales. Finding it in the atmosphere of a planet with possible oceans hinted at potentially similar processes occurring on this distant world as well. Methane was perhaps even more intriguing, as this molecule tends to be destroyed by reactions with starlight over relatively short cosmic timescales. For methane to persist in an atmosphere, something must be replenishing it continuously, either geological processes or, more intriguingly, biological activity below. On Earth, the vast majority of atmospheric methane is produced by living organisms, from bacteria to cattle grazing in fields. Of course, methane can also be produced by purely geological processes that don't involve life at all in any way. Volcanic activity and certain chemical reactions between rocks and water can release methane without any biological involvement whatsoever. Scientists were careful not to jump to conclusions about what the methane detection might mean for the possibility of life on the planet. What made the James Webb observations particularly significant was what they didn't find in the planet's atmosphere during their analysis. The data showed no evidence of ammonia, a molecule that would be expected if K2-18b were a Neptune-like world with a thick, gaseous envelope. The absence of ammonia supported the idea that this planet might have a defined surface, possibly a global ocean beneath its hydrogen-rich atmosphere. This combination of findings, carbon dioxide, methane, water vapor, and no ammonia, was consistent with a specific type of world that some scientists call a Hycean planet. The term combines hydrogen and ocean to describe a planet with a hydrogen-rich atmosphere above a water ocean, a type of world theorized but never directly observed until now. K2-18b seemed to fit this description remarkably well, based on all available evidence. The James Webb observations also allowed scientists to refine their models of the planet's atmosphere and surface conditions with greater precision. The first precision. Computer simulations suggested that the planet could have surface temperatures compatible with liquid water, perhaps somewhere between 0 and 40 degrees Celsius. These are temperatures that life on Earth tolerates quite comfortably, from polar seas to tropical lagoons across our world. The pressure at the surface would likely be higher than on Earth, but not necessarily crushingly so, depending on the model assumptions used. Some scenarios suggested pressures comparable to deep-sea environments on Earth, where life thrives despite conditions that would be lethal for surface-dwelling creatures like us. Other scenarios suggested more moderate pressures that might be hospitable to a wider range of potential biological forms.
Each new piece of information from James Webb helped narrow down the possibilities for what K2-18b might actually be like up close.
The data couldn't prove that life exists there, but it could show whether the conditions were at least compatible with life as we know it. So far, everything pointed toward a world that was at least plausibly habitable, a remarkable conclusion given how little we knew just a few years earlier. The scientific papers describing these findings generated significant media attention and public interest when they were released to the world. Headlines proclaimed the discovery of a potentially habitable ocean world, while scientists urged caution about over-interpreting the still limited data available. This tension between excitement and caution is typical of frontier science, where each new discovery raises as many questions as it answers. The James Webb Space Telescope continues to observe K2-18b and will likely gather additional data in the years ahead as its mission continues. Each new observation adds to our understanding of this fascinating world and helps refine our models of its atmosphere and surface conditions below. The picture that emerges will become clearer over time, though some mysteries may require future generations of telescopes to fully resolve. For now, the James Webb observations have established K2-18b as one of the most promising candidates for a habitable world beyond our solar system. The combination of water, carbon dioxide, and methane in its atmosphere paints a picture of a dynamic and chemically interesting planet worth studying for decades to come. Whatever secrets this distant ocean world holds, we are closer to understanding them than ever before in human history. In the next part, we'll explore one of the most tantalizing and controversial aspects of the James Webb findings, a possible detection that, if confirmed, could change everything we think about this distant world. Among all the molecules detected in K2-18b's atmosphere, one stands out as particularly intriguing and potentially significant for researchers. The James Webb observations showed a tentative signal that might indicate the presence of a molecule called dimethyl sulfide, often abbreviated as DM. If confirmed, this detection would be remarkable because, on Earth, dimethyl sulfide is produced almost exclusively by living organisms in our oceans. Dimethyl sulfide is a simple molecule containing 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom bonded together in a specific arrangement. On our planet, it is primarily produced by phytoplankton, the tiny photosynthetic organisms that form the base of marine food chains everywhere. When you smell that characteristic ocean scent at the seaside, what you're actually smelling is largely dimethyl sulfide released by countless microscopic organisms. The detection in K2-18b's atmosphere is tentative, meaning scientists are not yet certain that the signal is real, rather than instrumental noise. Confirming the presence of such a molecule requires multiple observations and careful analysis to rule out other explanations for the data collected. The scientific community treats such preliminary findings with appropriate caution, even while acknowledging their potential significance if validated. If dimethyl sulfide is genuinely present in the atmosphere of K2-18b, it raises fascinating questions about its origin on that distant world. On Earth, we know of no significant geological or chemical process that produces this molecule in quantities comparable to biological production rates. The simplest explanation for its presence would be that some form of life exists in the planet's ocean, producing dimethyl sulfide just as phytoplankton do here. However, scientists are careful to consider alternative explanations before concluding that life must be responsible for any particular observation made from so far away. The chemistry of an alien world could be very different from Earth's, with processes we haven't imagined producing molecules in unexpected ways and quantities. A hydrogen-rich atmosphere above a water ocean might allow chemical reactions that simply don't occur in Earth's nitrogen-oxygen atmosphere at all. The sulfur cycle on K2-18b is completely unknown, and it's possible that geological processes could produce dimethyl sulfide under certain conditions. Volcanic activity, interactions between water and rocks, or photochemical reactions in the upper atmosphere might all contribute to sulfur chemistry in ways we can't predict. Until we understand the planet's full chemical context, we can't definitively attribute dimethyl sulfide to biological activity alone. Still, the possibility that we might have detected a biosignature, a chemical sign of life, on another world is genuinely exciting for the scientific community. Biosignatures have long been discussed as potential ways to detect life on exoplanets from a distance, without needing to send spacecraft to visit them directly. If dimethyl sulfide can be confirmed on K2-18b, it would be a landmark moment in the search for extraterrestrial life. The concept of biosignatures is based on the idea that life modifies its environment in detectable ways that would be unlikely without biological activity. On Earth, the presence of large amounts of oxygen in our atmosphere is a biosignature, produced mainly by photosynthetic organisms over billions of years of evolution. An alien astronomer studying Earth from a distance might detect our oxygen and wonder whether life was responsible for its presence here. For K2-18b, dimethyl sulfide would serve a similar function as a potential indicator of biological activity occurring somewhere below the atmosphere. The molecule is reactive enough that it wouldn't persist for long without being continuously produced by some ongoing process or source. If it's there, something is making it, and the most straightforward explanation would involve ocean life of some kind. Astronomers plan additional observations of K2-18b to either confirm or refute the tentative dimethyl sulfide detection in coming years. The James Webb Space Telescope will likely observe more transits, gathering additional data that can be combined with existing observations for better precision and accuracy. Other telescopes and techniques may also contribute to this effort as technology continues to advance and improve over time. The uncertainty surrounding this detection is a normal part of science, at the frontier of human knowledge, where new discoveries are often initially unclear. It took years of careful work to confirm the presence of water vapor in the planet's atmosphere, and dimethyl sulfide may require similar patience. Scientists are comfortable with uncertainty in a way that can sometimes frustrate a public eager for definitive answers about alien life. What we can say with confidence is that K2-18b has become one of the most important targets in the search for life beyond Earth today. The combination of potentially habitable conditions and a tentative biosignature detection makes it a priority for continued observation and study by researchers worldwide. Whether or not the dimethyl sulfide signal is eventually confirmed, the planet has earned its place in the history of astrobiology. The search for life in the universe is a long and patient endeavor, requiring decades of careful observation and analysis to make real progress forward. Each new piece of evidence, even tentative ones like this detection, helps guide future research and telescope time toward the most promising targets. K2-18b will continue to be watched closely as humanity slowly unravels the mystery of whether we are alone in the cosmos. For now, the possible dimethyl sulfide detection remains one of the most tantalizing hints that something remarkable might be happening on this distant ocean world. The molecule that gives our oceans their characteristic smell might also be drifting through the atmosphere of a planet 124 light-years away. That possibility alone is enough to inspire continued exploration and wonder about what might exist beneath those alien skies so far away. Next, we'll explore the concept of Hycean worlds and what scientists believe K2-18b might actually be like beneath its thick atmosphere. The discoveries about K2-18b have given scientists an opportunity to explore a type of planet that may be common but has no equivalent in our own solar system. These hypothetical worlds are called Hycean planets, a term that combines the words hydrogen and ocean to describe their defining characteristics quite well. Understanding what a Hycean world might be like helps us imagine what conditions K2-18b could offer beneath its thick atmospheric blanket. The concept of Hycean planets was formalized in a scientific paper published in 2021 by a team of researchers at Cambridge University. They proposed that planets with hydrogen-rich atmospheres and water oceans could potentially support life under conditions quite different from Earth's familiar environment. These worlds would be larger than Earth, but smaller than Neptune, occupying a size range that is actually very common among known exoplanets. A key feature of Hycean worlds is their thick hydrogen atmosphere, which would create a strong greenhouse effect to warm the planet's surface. Hydrogen is a very effective greenhouse gas, trapping heat and raising temperatures above what the planet would experience with a thinner or different atmosphere. This greenhouse warming could allow liquid water to exist on planets that would otherwise be frozen solid at their distance from their star. The ocean beneath a Hycean atmosphere would likely be global, covering the entire surface of the planet without any continents or land masses rising above the waves. This is very different from Earth, where about 30% of the surface is covered by land and the remaining 70% by ocean waters. A Hycean world would be water everywhere you looked, with no beaches, no mountains, and no terrestrial landscapes at all to break the monotony. Such oceans could be incredibly deep, potentially hundreds of kilometers from surface to seafloor, in some regions of the planetary interior. The pressure at the bottom of such an ocean would be immense, far greater than anything found in Earth's deepest trenches beneath the waves. At sufficient depth and pressure, water might take on exotic forms, potentially transitioning to high-pressure ice phases even at temperatures above freezing. The surface of a high-Ocean ocean would experience different conditions, with more moderate pressures and temperatures potentially compatible with complex chemistry and biology. Scientists have calculated that surface temperatures on K2-18b could range from near freezing to comfortably warm, depending on various factors and modeling assumptions. These temperatures are well within the range that life on Earth occupies, from polar seas to tropical waters across our planet's oceans. One interesting aspect of high ocean worlds is that they might remain habitable even if they are tidally locked to their parent star, as K2-18b likely is. The hydrogen atmosphere would efficiently distribute heat from the day side to the night side, preventing extreme temperature differences across the planet's surface. Ocean currents would also help transport heat around the planet, smoothing out temperature variations even further over time. This means that life on a Haitian world wouldn't necessarily be confined to a narrow twilight zone between frozen and boiling hemispheres, as some scenarios suggest. Instead, large portions of the planetary ocean might maintain temperatures suitable for liquid water and potentially for life to thrive comfortably. The habitability of such worlds could extend across much of their surface area, rather than being limited to special regions alone. The chemistry of a Haitian ocean would likely be quite different from Earth's seas due to the hydrogen-rich atmosphere above the water's surface. Dissolved gases, chemical reactions, and potential nutrients would all be influenced by this different atmospheric composition in various ways over time. Life that evolved in such an environment would face different challenges and opportunities than life in Earth's nitrogen-oxygen atmosphere does today. Scientists have speculated about what kinds of organisms might thrive in a Haitian ocean if life exists there at all in some form. Simple microbial life seems most likely, similar to the bacteria and archaea that dominate Earth's biosphere by sheer numbers and biomass, if not by visibility. More complex life forms are possible, but would require very specific conditions to evolve and flourish over billions of years of planetary history. The Haitian planet hypothesis has significant implications for the search for life in the galaxy and where we should focus our attention. If these hydrogen ocean worlds can support life, then the number of potentially habitable planets in the Milky Way is much larger than previously estimated. Red dwarf stars, which are the most common stellar type, might host many such worlds in their habitable zones, waiting to be discovered. K2-18b fits the profile of a Haitian world remarkably well, based on everything we've observed and measured so far. Its size, mass, atmospheric composition, and position in the habitable zone all align with the theoretical predictions for this planetary type quite closely. While we can't be certain without direct observation of its surface, the evidence strongly suggests we may be looking at the first confirmed Haitian planet. The concept remains somewhat controversial among scientists, with some researchers arguing that conditions on such planets might not actually be favorable for life. High atmospheric pressure, unusual chemistry, and other factors could create environments that are hostile, despite having liquid water available at the surface. As with many questions in astrobiology, we won't know for certain until we gather much more information about these distant worlds through continued observation. For now, The Hycean hypothesis provides a useful framework for thinking about what K2-18b might be like beneath its thick, cloudy skies. It suggests a world of endless ocean beneath a heavy hydrogen atmosphere, possibly warm enough for liquid water, and perhaps even hospitable to some form of life. This framework guides scientific research and helps focus telescope time on the most important questions we can address with available technology. In the next part, we'll let our imagination explore what this global ocean might actually be like, a world without shores or continents in sight. Imagine standing on the surface of K2-18b. Though of course, no human could actually survive such an experience without extraordinary protection from the environment. There would be no land visible in any direction, only water, stretching to every horizon beneath a sky thick with hydrogen and clouds overhead. The concept of direction would lose much of its meaning on such a world, with no landmarks to navigate by anywhere you looked around. The ocean beneath you might extend downward for hundreds of kilometers, deeper than any abyss that exists on Earth, by a tremendous margin. For comparison, the Mariana Trench on Earth reaches about 11 kilometers at its deepest point, which would be merely a shallow coastal region on this planetary scale. The pressure at the bottom of K2-18b's ocean could be millions of times greater than the pressure at sea level on our own world. At such extreme depths, water behaves in ways that seem almost alien compared to our everyday experience of it flowing from taps and falling as rain. High-pressure phases of ice can form even at temperatures above freezing, creating exotic forms of solid water deep in the planetary interior. These ice phases have names like Ice 7 and Ice 10, structures that only exist in laboratories on Earth under extreme conditions we rarely encounter. Near the surface, however, conditions would be more familiar in some ways, with liquid water responding to temperature and pressure much as it does in our oceans here. Waves might roll across the surface, driven by winds in the thick atmosphere above, though their character would differ from Earth waves due to different gravity and air density. The water itself would likely be warmer than Earth's average ocean temperature, heated by the greenhouse effect of the hydrogen atmosphere overhead. What color would this ocean be when viewed from above its surface by some hypothetical observer floating in the thick clouds above? Earth's oceans appear blue because water absorbs red light more readily than blue, allowing blue wavelengths to scatter and reach our eyes from below. The same physics would apply on K2-18b, potentially giving its ocean a similar blue or blue-green appearance, depending on what might be dissolved or living in the water. The dim reddish light from the star K2-18 would cast everything in a warm glow quite different from the bright white light of our own sun. This light would penetrate the ocean's surface and illuminate the upper layers, though it would fade quickly with depth as water absorbed it progressively. Below a certain point, perhaps just a few hundred meters down, permanent darkness would reign throughout the vast depths of the planetary ocean below. In this darkness, any life that existed would need to rely on chemical energy rather than sunlight to power its metabolism and survival needs. On Earth, entire ecosystems exist around hydrothermal vents on the deep ocean floor, where no sunlight ever reaches the organisms living there comfortably. Similar energy sources might exist on K2-18b, where geological activity could provide heat and chemicals to support life in the depths. The chemistry of this alien ocean would depend on the rocks at its floor and the gases dissolved from the atmosphere above its churning waves. If the seafloor contains minerals similar to those on Earth, water-rock interactions could produce hydrogen and other chemicals that microbes might use for energy generation. Without more information about the planet's interior composition, we can only speculate about what resources might be available for potential life forms. Storms on this ocean world could be truly immense, driven by the thick atmosphere and possibly by the temperature difference between the day and night hemispheres of the planet. Hurricane-like systems might persist for months or years, their winds driving massive waves across the planet's surface, around and around in endless circuits. Yet from within the depths, these surface storms would be muted, their fury absorbed by the weight of water pressing down from above. The tides on K2-18b would be minimal or non-existent if the planet is tidally locked to its star, as scientists suspect it likely is. With no moon to raise tidal bulges, and with one face always pointing toward the star, the regular rising and falling of water would not occur as it does on Earth. This might create a more static ocean circulation pattern, dominated by temperature-driven currents, rather than tidally driven flows moving water around the globe. Life in such an ocean, if it exists at all in some form we might recognize as living, would have evolved under conditions utterly unlike those on Earth's continents and coastlines. There would be no intertidal zones where organisms adapted to both water and air could emerge and eventually colonize land over evolutionary time. Any life would be fully aquatic, with no opportunity to develop toward land-dwelling forms, as happened on Earth during our evolutionary history. The absence of land also means no weathering of continental rocks to release nutrients into the ocean, as happens on Earth through rivers and erosion constantly. Whatever nutrients existed in the primordial ocean when the planet formed would need to be recycled efficiently for life to persist over billions of years. Alternatively, hydrothermal vents or other geological processes might continuously supply new materials to keep the ocean chemically active and potentially hospitable to life. This global ocean remains beyond our direct observation, existing only in models and imagination based on the atmospheric data we've collected from afar. Yet the picture that emerges is consistent and compelling, a world of water on a scale that dwarfs anything in our own solar system's inventory. Whether life swims in those dark depths or the ocean remains sterile, the planet represents a new type of world waiting to be understood. The atmosphere of K2-18b is thick and heavy, dominated by hydrogen with significant amounts of water vapor, carbon dioxide, and methane, mixed throughout its layers. This atmospheric blanket extends far above the ocean surface, creating a sky very different from the thin blue canopy that covers our own world daily. Looking up from the ocean surface, if such a thing were possible, you would see something quite unlike any sky on Earth. Because the planet is likely tidally locked to its star, the sky would appear fundamentally different depending on where on the planet you happen to be observing from. On the day side, the dim red star K2-18 would hang motionless in the sky, never rising or setting as the sun does on Earth. The light would be constant and unwavering, a perpetual noon that has lasted for billions of years and will continue for trillions more in the future. This starlight would be shifted toward the red end of the spectrum, giving everything a warm, amber glow, quite different from the harsh white light of our own sun at midday. Shadows would be softer and less distinct under this diffuse reddish illumination, and colors would appear different to any eyes evolved to see in this light. The perpetual day would feel eternal, a frozen moment of twilight-like illumination stretching on without beginning or end. On the night side of the planet, the sky would be completely dark, except for the distant stars that dot the galaxy beyond this solar system. No starlight from K2-18 would ever reach this hemisphere directly, leaving it in permanent darkness, unbroken by any dawn on the horizon. The only light might come from the faint glow of the atmosphere itself, redistributed from the day, side by powerful winds circulating around the planet constantly. Between these two extremes lies a twilight zone, a ring around the planet, where the star hovers perpetually near the horizon in the sky above. Here the light would be dim and reddish, similar to the light on Earth, just after sunset or just before sunrise each day. This twilight region might have its own unique conditions, potentially the most moderate temperatures and the most stable weather patterns on the entire planet's surface. The thick hydrogen atmosphere would be in constant motion, driven by the temperature difference between the scorching day side and the frigid night side of the planet. Powerful winds might blow from day to night at high altitudes, cooling as they traveled and eventually sinking down on the dark hemisphere before returning. This circulation pattern would help distribute heat around the planet, moderating the extreme temperature contrasts that might otherwise exist between hemispheres. Clouds would likely be a permanent feature of the atmosphere, though their composition might differ from the water clouds familiar to us on our own world. Water clouds could exist at certain altitudes, but the hydrogen-rich atmosphere might also host exotic cloud types made of other materials and chemical compounds. These clouds might be thick enough to completely obscure the star from much of the ocean's surface, creating a dim, diffuse light everywhere below them. Weather on such a planet would be driven by processes both familiar and strange compared to Earth's meteorology that we study and experience. Convection, condensation, and wind patterns would operate according to the same physical principles, but under very different conditions than we experience here. The results might include storms of unprecedented size and duration, or, alternatively, a surprisingly stable and calm atmospheric state, depending on exact conditions. The thick atmosphere would efficiently trap heat through the greenhouse effect, keeping the ocean surface warm enough for liquid water to exist comfortably. This greenhouse warming is essential for making the planet potentially habitable at its distance from its dim red star in deep space. Without the insulating effect of hydrogen, the planet would likely be frozen solid, its ocean locked beneath kilometers of permanent ice forever. Sound would travel differently through this thick hydrogen atmosphere, with acoustic properties quite unlike those on Earth that we're accustomed to experiencing. Sounds might travel faster and farther, and the pitch of noises might be shifted in unexpected ways due to the different molecular composition. Any creatures with hearing on this world would perceive their environment through a very different acoustic landscape than we experience on Earth daily. The sky color itself would depend on how different wavelengths of light scatter through the hydrogen atmosphere and whatever particles it contains floating within. On Earth, our sky appears blue because nitrogen and oxygen scatter blue light more effectively than other colors in the visible spectrum. A hydrogen atmosphere might produce different colors, potentially reddish or orange hues that would complement the dim light of the red dwarf star above. As we imagine these alien skies, we're reminded how different other worlds can be from the familiar environment we know on our own planet. Earth's thin atmosphere, its day-night cycle, its blue skies, none of these features are universal, and many planets operate under very different rules. K2-18b represents one such alternative, a world that might be habitable, but in ways that challenge our assumptions about what habitable means in practice. The eternal nature of this sky, whether blazing with constant starlight or wrapped in permanent darkness, creates a timelessness that our rotating Earth never experiences. Days and nights, the rhythm that has governed life on Earth for billions of years, simply don't exist in the same way on this tidally locked world. Any life that evolved there would have no concept of sunrise or sunset, experiencing instead the endless constancy of wherever it happened to live. In the next part, we'll consider the profound question that underlies all our interest in this distant world: whether life could exist in its dark, oceanic depths. Everything we've learned about K2-18b leads inevitably to a single profound question that has captivated human imagination for centuries. Could life exist on this distant ocean world, swimming through waters that have never reflected the light of our own familiar sun? The question may not have a definitive answer for generations, but we can explore what science tells us about the possibilities involved. Life as we know it requires a few key ingredients, liquid water being perhaps the most fundamental and non-negotiable requirement of all biological processes. Water serves as the solvent in which biochemical reactions occur, and its unique properties make it ideal for the complex chemistry of living systems everywhere. K2-18b appears to have liquid water in abundance, potentially covering its entire surface in a global ocean of tremendous depth. Beyond water, life needs energy to power its metabolism and drive the chemical reactions that sustain biological processes over time. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly by eating organisms that photosynthesize for their energy. But life on Earth has also found ways to thrive without sunlight, using chemical energy from geological sources in the deep ocean and underground. The dim reddish light from K2-18 would penetrate only the upper layers of its planetary ocean, leaving the vast depths in permanent darkness forever. Any photosynthetic life would be confined to a thin surface layer, while the majority of the ocean would need to rely on other energy sources. Hydrothermal vents, similar to those found on Earth's ocean floors, could potentially provide chemical energy to support entire ecosystems independent of starlight overhead. Life also requires certain elements to build its molecular machinery, including carbon, nitrogen, phosphorus, and various other substances found throughout Earth's biosphere. The presence of carbon dioxide and methane in K2-18b's atmosphere suggests that carbon is available in this planetary system for building organic molecules. Other essential elements might come from rocks on the ocean floor, dissolved into the water over billions of years of chemical interaction. The conditions on K2-18b are extreme by Earth standards, but life on our own planet has proven remarkably adaptable to challenging environments worldwide. Extremophiles, organisms that thrive in conditions once thought impossible for life, have been found in boiling hot springs, frozen Antarctic lakes, and crushing deep-sea environments. These discoveries have expanded our understanding of where life can exist and suggest that habitability is a broader concept than we once imagined. The high pressure at depth in K2-18b's ocean would challenge life, but not necessarily prevent it from existing there in some form. Pressure itself is not inherently lethal to living organisms, as demonstrated by the diverse life found in Earth's deepest trenches and around hydrothermal vents. What matters more is whether organisms can adapt their biochemistry to function under such conditions over evolutionary timespans of millions of years. Temperature is another crucial factor, and the surface of K2-18b appears to be within a habitable range based on current modeling efforts. Temperatures between 0 and 40 degrees Celsius are comfortable for a wide range of Earth life, from polar bacteria to tropical fish in our oceans. If the planet's surface ocean maintains such temperatures, it would not pose a thermal barrier to life as we understand it biochemically. The hydrogen-rich atmosphere creates a chemical environment quite different from Earth's, and any life would need to be adapted to these specific conditions. On Earth, organisms have evolved to breathe oxygen, or to survive in oxygen-free environments, depending on their ecological niche and evolutionary history. Life on K2-18b might use hydrogen directly in its metabolism, or it might have evolved entirely different biochemical pathways for energy generation. The tentative detection of dimethyl sulfide adds a tantalizing possibility that life might already exist in this distant ocean, awaiting confirmation. If confirmed, this molecule would be difficult to explain without invoking biological activity of some kind, producing it continuously. But even if dimethyl sulfide turns out to be absent or explainable by non-biological processes, the conditions remain potentially suitable for life to exist. We should be cautious about assuming that life must exist wherever conditions permit it, as we have only one example of life arising and evolving over time. Earth may have been lucky in ways we don't fully understand, or life may be an inevitable consequence of the right chemistry given enough time. Until we find life elsewhere, or definitively rule it out in promising locations, the question remains genuinely open and fascinating. The search for life on K2-18b and similar worlds is not just a scientific endeavor, but also a deeply human quest for understanding our place in the universe. Finding life elsewhere would transform our perspective on existence itself, confirming that the universe is capable of producing living things more than once. Even finding no life, while perhaps disappointing, would teach us something important about how rare and precious our own existence might be. For now, K2-18b remains a world of possibility, a place where the conditions for life might be met, but where no direct evidence of life has been confirmed. It represents our best current example of a potentially habitable world quite different from Earth, expanding our conception of where to look for life. The question of whether something swims in its dark oceans remains one of the most compelling mysteries in all of science today. In the next part, we'll return to the light of the red sun and imagine what it might be like to exist beneath its eternal, warm glow. The star K2-18 is a quiet presence in the cosmos, a red dwarf that has burned steadily for billions of years and will continue for trillions more. Its light, though dim compared to our sun, has illuminated its planetary system continuously since before life arose on Earth in our own solar system. Now we pause to consider what this ancient light might mean for anything that exists beneath it on the ocean world we've been exploring. Red dwarf stars emit most of their energy in the infrared and red portions of the electromagnetic spectrum, wavelengths that feel warm to human skin. The visible light they produce is shifted toward orange and red, creating an illumination that would feel like perpetual sunset to human eyes observing it. This warm light would color everything it touched, casting the world in hues that we associate with evening calm and the approach of restful night on Earth. If you could somehow float above the ocean surface on K2-18b's day side, the light would feel different from any sunlight you've experienced on our own world. There would be no harsh white glare, no need to shade your eyes from overwhelming brightness, as we do on sunny Earth afternoons. Instead, the illumination would be gentle and suffused, more like firelight than the blazing noon of a summer day back home. The color of this light matters for more than aesthetics, as it would influence any photosynthetic life that might evolve to capture stellar energy for its metabolism. Plants on Earth evolved to absorb red and blue light efficiently, because these wavelengths are abundant in sunlight and energetically useful for photosynthesis. Organisms on K2-18b would need to adapt to the different spectrum available, potentially developing pigments quite unlike the green chlorophyll we're familiar with. Some scientists have speculated that photosynthetic life under a red dwarf might appear black to human eyes, absorbing all available wavelengths to maximize energy collection. Others suggest that organisms might appear red or orange themselves, reflecting wavelengths that are less useful for their metabolism back into the environment. Without actually observing such life, we can only guess at the rainbow of colors that alien biology might display. The warmth of this red light would help maintain liquid water on the planet's surface, working in concert with the hydrogen atmosphere's greenhouse effect below. A delicate balance exists between stellar input, atmospheric retention, and heat distribution that keeps the ocean from freezing or boiling away completely. This balance has apparently held for billions of years, providing stable conditions that could, in principle, support the long evolution of complex life forms. The star K2-18 has a close relationship with its planet, the two bodies gravitationally bound in an eternal dance through space together. Their proximity means that the star's gravity has likely locked the planet's rotation, creating the perpetual day and night hemispheres we discussed earlier, in detail. This gravitational embrace shapes everything about the planet's environment, from its atmosphere to its potential habitability for life. Unlike our Sun, which will exhaust its hydrogen fuel in roughly 5 billion years, K2-18 will continue burning for an almost inconceivable length of time. Red dwarfs are the most fuel-efficient stars, burning their hydrogen slowly and steadily over timescales that dwarf the current age of the universe itself. Any life on its ocean world would have vast stretches of time available for evolution and development far beyond what Earth's biosphere will experience. This longevity creates interesting possibilities for what might evolve on worlds orbiting red dwarf stars over cosmic timescales of existence. If life arose early in the planet's history, it would have had billions of years already to diversify and possibly develop complexity we can barely imagine. And it would have trillions of years still ahead, an almost endless future in which anything might become possible given enough time. The light of K2-18 will continue falling on its ocean world long after our Sun has died and Earth has become uninhabitable for all life. This is a humbling thought, reminding us that the cosmos operates on timescales far beyond human comprehension or experience in our brief lives. The red dwarf and its planet will persist as cosmic companions when all memory of humanity might have faded from the universe entirely. We find ourselves drawn to this distant world, partly because its star is so patient, so enduring, so fundamentally different from our own bright but fleeting sun overhead. There's something peaceful about contemplating a light that doesn't rush, that doesn't burn too hot or too fast through its fuel reserves. The red glow of K2-18 seems almost designed for contemplation, for slow thoughts and long rests beneath the eternal sky. Now we'll step back to consider the vast distance between Earth and this ocean world, the 124 light-years that separate us. The distance to K2-18b is 124 light-years, a number that is easy to say, but almost impossible to truly comprehend in human terms. A light-year is the distance that light travels in 1 year, roughly 9.5 trillion kilometers of empty space between any 2 points. Multiply that by 124, and you have a gulf of distance that separates this ocean world from our own blue planet spinning around the sun. If you could somehow travel at the speed of a commercial airplane, around 900 kilometers per hour, the journey would take more than 150 million years. Generations beyond counting would live and pass away aboard such a vessel, never knowing the departure point or the destination that lay ahead. The entire span of human civilization, from the first cave paintings to tonight, would repeat itself thousands upon thousands of times during that crossing. Even light, the fastest thing in the universe, requires 124 years to make the journey from that distant red star to Earth. The photons that astronomers capture in their telescopes tonight began their journey before anyone listening to this was born, traveling silently through the vacuum of space. They pass through regions where no planet orbits, no star shines, and no warmth exists, just the cold, patient darkness between solar systems. When the James Webb Space Telescope observed K2-18b, it was not looking at the planet as it exists right now in this present moment. It was looking at the planet as it existed 124 years ago, when that light first left the atmosphere of this distant ocean world. If something changed there today, a great storm, a shift in the clouds, or something we cannot imagine, we would not know about it until the year 20149. This delay is one of the strange realities of astronomy, a field built entirely on patience and the willingness to accept that all observations are historical. We never see the universe as it currently is, only as it was when its light began traveling toward us across the emptiness of space. The farther we look, the deeper into the past we peer, and the more we must trust that what we observe still holds some truth. For K2-18b, 124 years is a relatively short delay, a blink of an eye in cosmic terms. The planet star has been burning for billions of years and will continue for billions more, barely changing in that sliver of time between observation and reality. Whatever ocean exists on that world, whatever atmosphere wraps around it, almost certainly remains much the same as when that ancient light departed. The patience required to study such distant worlds is something that defines the entire practice of astronomy, setting it apart from sciences that can touch their subjects. A biologist can hold a specimen in their hands, examine it under a microscope, and repeat experiments within the span of an afternoon, if needed. A geologist can chip away at rock formations, carry samples back to a laboratory, and analyze their composition with instruments that offer immediate, tangible feedback. But astronomers cannot visit the worlds they study, cannot collect samples from atmospheres 124 light-years away, cannot touch the surfaces of planets that exist. They can only watch and wait, gathering photons one by one across months and years of careful, methodical observation from telescopes perched on mountains or floating in orbit. The data they collect represents a kind of cosmic mail, messages that were sent long ago and have only just arrived at our doorstep. This is why each observation of K2-18b represents something precious, a rare opportunity to learn about a world we may never physically reach. Every spectrum, every measurement of light passing through that hydrogen-rich atmosphere carries information that traveled for more than a century to reach us here. Scientists treat such data with immense care, analyzing it from every possible angle, knowing that follow-up observations require more time, more telescope hours, and more waiting. The constellation Leo, where the star K2-18 resides, has been known to humanity for thousands of years and carries stories from nearly every ancient civilization. Babylonian astronomers recorded its position. Greek mythology connected it to the Nemean lion of Heracles, and cultures around the world saw patterns in those same scattered points of light. None of them could have imagined that within this familiar constellation lay a world covered in water, orbiting a star too dim to see without a telescope. This is one of the quiet miracles of modern astronomy, the way it reveals hidden treasures within regions of the sky that our ancestors thought they knew completely. The stars they named and wove into stories were only the brightest, the most obvious, the ones that demanded attention with their brilliance. Behind them, around them, woven invisibly through the darkness, are billions of fainter stars that host their own families of planets, spinning in silence. K2-18 is one of those hidden stars, a red dwarf so dim that no human eye has ever seen it directly without technological assistance. Yet this unassuming point of light hosts one of the most intriguing worlds we have ever discovered, a planet that challenges our assumptions about where oceans can form. The ancients who named Leo could never have dreamed that such wonders lay hidden within the lion's celestial territory, waiting patiently to be found. The space between Earth and K2-18b is not truly empty, though we often describe it that way for the sake of simplicity and convenience. Scattered through that 124 light-year gulf are particles of dust, wisps of hydrogen gas, and the occasional wandering comet or asteroid drifting between star systems. These travelers move so slowly relative to the distances involved that they might take millions of years to cross from one stellar neighborhood to another. Cosmic rays also stream through this space, high-energy particles ejected from distant supernovae and other violent events that occurred long before our solar system even formed. They travel at nearly the speed of light, carrying energies that would be dangerous to unprotected astronauts, but that pose no threat to planets wrapped in protective magnetic fields and thick atmospheres. Some of these particles have been traveling for millions of years, crossing the galaxy in paths that occasionally intersect with the space between us and this distant ocean world. If you could somehow freeze time and travel that 124 light-year distance instantaneously, you would find mostly nothing along the way, and that nothing would be profound. Vast stretches of space where no star shines, where temperatures hover just a few degrees above absolute zero, where silence is so complete that the concept of sound loses all meaning. This is the medium through which light must travel to bring us news of distant worlds, and it does so without complaint, without interference, for over a century. The loneliness of interstellar space is difficult to truly appreciate from our position here on Earth, surrounded by air and light and life. We live on a planet teeming with activity, where something is always moving, growing, changing, or making noise in one way or another. Step outside on any night and you can see the moon, spot a few planets, and trace the familiar patterns of stars that have guided humanity for millennia. But if you were somehow transported to a point halfway between Earth and K2-18b, you would see stars in every direction, yet none of them would be close. The sun would be a dim point of light, barely distinguishable from the millions of other stars scattered across the blackness of that cosmic ocean. The star K2-18 would be equally faint in the opposite direction, offering no warmth, no guidance, just another pinprick in the endless dark. This is the true nature of the universe at the scale we are considering tonight. A vast archipelago of islands separated by oceans of emptiness, so large they defy imagination. Each star system is its own isolated world, connected to others only by the light it sends outward and the light it receives after years or centuries of travel. We are fortunate to live in an age when we can detect that light and decode its messages, learning about places we will never visit in person. The light from K2-18 that reaches Earth tonight began its journey in the year 1901, when horse-drawn carriages still filled city streets and the Wright brothers had not yet achieved powered flight. Queen Victoria had just passed away. Theodore Roosevelt was about to become President of the United States, and the world was on the cusp of changes that no one could have predicted. That light traveled through space while humanity invented aeroplanes, fought world wars, landed on the moon, and built the very telescopes that would eventually capture those ancient photons. By the time that light arrives at the James Webb Space Telescope, everything on Earth has transformed beyond recognition in ways that would seem like magic to people from that earlier era. We have split the atom, walked on the lunar surface, and sent robotic explorers to the outer reaches of our solar system since that light departed. Yet the photons themselves carry no knowledge of these changes, no awareness that their destination has evolved so dramatically during their long journey. There is something humbling about this realization. The way that light simply travels, indifferent to the dramas unfolding at either end of its long journey through space. It does not care that wars were fought, that civilizations rose and fell, that a species evolved to build instruments capable of catching it. The light just moves forward at 300,000 kilometers per second, following the geometry of space-time, until something finally stops it and reads the message. The astronomers who study K2-18b today are not the same ones who will see the results of observations planned for decades in the future. Careers in astronomy span perhaps 40 or 50 years, a tiny fraction of the timescales involved in truly understanding a world 124 light-years away. Young graduate students who begin working on exoplanet atmospheres today may be retired before the full picture of this ocean world finally comes into focus. This is why astronomy is fundamentally a collaborative endeavor, passed down through generations like a vast, slow-moving relay race across the centuries. The data collected today will be analyzed by scientists not yet born, using techniques and technologies that we cannot currently imagine or predict. Somewhere in the future, a researcher will build upon everything we have learned and take one more step toward understanding what K2-18b truly is. The patience this requires is extraordinary, a willingness to contribute to a project whose completion you will never see and whose final answers you will never know. Yet astronomers accept this reality with grace, understanding that they are part of something larger than any individual career or lifetime could possibly contain. They add their observations to the growing archive, trusting that future generations will continue the work with the same dedication and curiosity that drives them now. When you look up at the night sky, you are seeing the past in every direction. Light that left its source years or centuries or millennia before you were born. The stars you see are not where they appear to be, having moved in their orbits around the galaxy since their light began its journey toward Earth. The constellations we know are temporary patterns, slowly shifting over thousands of years as stars drift through space on their own independent paths. K2-18b is out there right now, in a present moment we cannot observe, spinning through its 33-day orbit around its dim red star somewhere in the direction of Leo. Its ocean, if it exists, is doing whatever oceans do on such a world. Perhaps churning with currents, perhaps lying eerily still beneath that thick hydrogen atmosphere. We will not know what is happening there today until the year 21420, when the light from this present moment finally completes its long journey to our waiting telescopes. This is the strange, beautiful limitation of our position in the universe, forever catching up to a present that has already become the past by the time we perceive it. Yet rather than frustration, this delay invites a kind of peace, a reminder that the universe operates on timescales that dwarf our hurried human concerns. The ocean world will still be there when tomorrow's light finally arrives, and the day after that, and for billions of years to come. The distance to K2-18b ensures that we will likely never send a spacecraft to visit it, at least not with any technology we can currently envision or build. Even traveling at 1/10 the speed of light, a velocity far beyond our current capabilities, the journey would take over 1,200 years to complete. Any probe we launched would arrive to find a humanity so transformed by time that the original mission might be forgotten entirely, lost in the long sweep of history. This means that everything we learn about this ocean world will come from light, from the patient collection of photons that have made the century-long journey across space. We will study its atmosphere, model its climate, search for biosignatures, and piece together its story entirely from afar, like archaeologists reconstructing a civilization from scattered fragments. It is astronomy at its most fundamental, the art of understanding through observation alone, without ever touching what we study. And perhaps there is something appropriate about this limitation, a built-in humility that keeps us honest about our place in the cosmic order of things. We are not conquerors of the universe, not explorers who can plant flags on every world we discover, but rather witnesses to its grandeur from our small blue home. K2-18b will keep its secrets close, revealing only what it chooses to share through the light it sends our way. The distance between us is vast, 124 light-years of mostly empty space, stretching through the constellation Leo toward a dim red star and its remarkable planet. Yet that distance has not prevented us from learning extraordinary things about this distant ocean world, from detecting water vapor in its atmosphere to sensing the possible presence of molecules that on Earth are made only by life. Across that impossible gulf, information flows toward us at the speed of light, carrying news of a world we can only imagine, inviting us to wonder what secrets still remain hidden beneath those alien skies. The story of K2-18b is, in many ways, just beginning, a single chapter in a much larger book that humanity is slowly learning to read and understand. We have detected an ocean world, sensed the chemistry of its atmosphere, and begun to imagine what conditions might exist on its surface, far below those hydrogen clouds. But so much remains unknown, so many questions still waiting for answers that may take decades or centuries to fully reveal themselves to patient observers. This is the nature of discovery at the edge of human knowledge, where every answer opens doors to new questions that we had not thought to ask before. The scientists who study this world today are pioneers in the truest sense, mapping territories that no human has ever seen or touched, with instruments designed to catch ancient light. Their work continues even as you listen to these words. Telescopes around the world and in orbit gathering more data about this remarkable planet, spinning around its dim red star. For now, what we know is extraordinary enough to fill the imagination with wonder and the mind with a quiet, settled sense of awe. A world covered in ocean, wrapped in hydrogen, orbiting a star that will shine for trillions of years. This is not science fiction, but observed reality, confirmed by multiple independent teams. The universe has revealed to us a place unlike anything in our solar system, expanding our understanding of where water can exist and life might someday be found. The ocean of K2-18b, if our models are correct, has existed for billions of years and will continue for billions more beneath that perpetual sky. Unlike Earth's oceans, which formed over hundreds of millions of years as the planet cooled and water vapor condensed, this ocean may have been present almost from the beginning. The hydrogen-rich atmosphere that blankets the planet creates conditions that trap heat efficiently, maintaining liquid water even at the cool distance from its dim red star. Imagine, if you will, an ocean with no memory of land, no shorelines where waves have ever broken, no continents to divide its waters into separate seas. This is a world where water is not a feature of the landscape, but the landscape itself, stretching in every direction without interruption or boundary. The concept of across the ocean loses meaning when the ocean is everything, when there is no other side to reach. Beneath the surface of this global sea, pressure builds with every kilometer of depth, conditions growing more extreme as you descend toward the bottom that may not exist. Some models suggest the ocean is so deep that water at the bottom transforms into exotic forms of ice, compressed by unimaginable pressure into solid states that remain stable even at high temperatures. This ice would not be cold as we understand cold, but rather a product of pressure so intense that molecules are forced into crystalline structures against their natural tendency to remain liquid. The sky above this ocean world would be like nothing any human has ever seen, filtered through a thick atmosphere and lit by the orange-red glow of a small, cool star. If you could somehow float on those alien waters and look upward, you might see clouds of hydrogen and methane drifting slowly across a hazy sky of unfamiliar colors. There would be no blue, no familiar scattering of sunlight that gives Earth's sky its characteristic hue during clear daylight hours. The star K2-18 would appear larger than our sun does from Earth, but this is only because the planet orbits so close to its dim parent star. Despite appearing larger, it would provide less total light, casting the world in perpetual twilight by our standards, a soft glow that never quite reaches the brightness of an overcast afternoon on Earth. Life on such a world, if it exists, would have evolved under these gentle lighting conditions, perhaps developing senses we cannot imagine. The color of that light would shift everything we know about vision and appearance, bathing the world in wavelengths that lean toward the red end of the spectrum. Plants on Earth are green because they reflect the wavelengths of light they do not use for photosynthesis, but life under a red dwarf might be different entirely. Some scientists speculate that photosynthetic organisms on such worlds might appear black, absorbing every available photon from their dim star to maximize energy capture. Whether life exists on K2-18b remains one of the great unanswered questions, a mystery that will occupy researchers for years and perhaps generations to come. The detection of dimethyl sulfide, if confirmed by future observations, would be a remarkable piece of evidence pointing toward biological processes beneath those alien clouds. But science requires confirmation, replication, and the careful elimination of alternative explanations before any conclusion can be considered reliable. The search for life beyond Earth is perhaps the most profound scientific endeavor humanity has ever undertaken, a question that touches philosophy, religion, and our deepest sense of identity. If we discover that life arose independently on another world, it would suggest that biology is not a cosmic accident, but rather a natural consequence of chemistry given sufficient time. The universe would transform from a vast, lonely emptiness into a garden of possibility, filled with potential that we are only beginning to recognize. K2-18b offers one of our best opportunities to make such a discovery, a world with water, organic molecules, and conditions that might support biochemistry as we understand it. It is not the only candidate. Astronomers have identified dozens of potentially habitable worlds, but it is among the most accessible to our current observational capabilities. The James Webb Space Telescope can study its atmosphere in detail, searching for the chemical fingerprints that might reveal the presence of living processes. The search continues even as you listen, telescopes turning toward targets across the sky, gathering data that will take months or years to fully analyze and understand. Somewhere, a graduate student is writing code to process spectral observations of a distant world, looking for patterns that might indicate something remarkable beneath alien clouds. Somewhere else, a senior astronomer is reviewing results, double-checking calculations, preparing to publish findings that will add another small piece to the growing puzzle. This is how knowledge advances, not in sudden revelations, but in gradual accumulation, each small discovery building upon those that came before it over generations of careful work. The story of K2-18b will unfold slowly, over decades rather than months, as observations pile up and understanding deepens in the patient way that science operates. There will be surprises along the way, there always are, and some of our current assumptions will likely prove incorrect. But this uncertainty is not a weakness of the scientific process. Rather, it is one of its greatest strengths that separates it from dogma and superstition. Science welcomes correction, embraces new evidence, and changes its conclusions when the data demands it, even when those changes are uncomfortable or unexpected. Whatever K2-18b truly is, ocean world, something else entirely, or something we cannot yet imagine, science will eventually find its way to the truth. The night sky above you tonight, wherever you are, contains more worlds than all the humans who have ever lived, a number so vast it approaches the meaningless and incomprehensible. Each star you can see with your naked eye hosts its own family of planets, and beyond those visible stars lie billions more, stretching across the galaxy like sand on an infinite shoreline. K2-18b is just one world among this countless multitude, one ocean among perhaps millions of alien seas that dot the cosmic landscape. Yet this one world has captured our attention, drawn our curiosity, and inspired us to build instruments capable of studying its atmosphere across 124 light-years of void and emptiness. It represents something important about the human spirit, this drive to understand places we cannot visit, to imagine worlds we will never touch with anything but light. We are a species that asks questions, and the universe, in its patient, indirect way, sometimes provides answers. The light from K2-18b that will reach Earth tomorrow is already on its way, traveling through the darkness at 300,000 kilometers per second, carrying information about conditions that exist right now on that distant ocean world. That light will continue to arrive for as long as the star shines, a continuous stream of data that future generations will collect and analyze with technologies we cannot predict. The conversation between humanity and this distant world has only just begun, and it will continue for as long as we remain curious enough to listen to what the universe whispers. As you rest tonight, that distant ocean continues its slow rhythms beneath hydrogen skies, unmarked by any observer, unknown to any mind that we can confirm with certainty exists. Currents may flow through its depths, driven by heat from below or radiation from above, moving water that has never known the touch of land or the disturbance of a shore. If creatures swim in those dark waters, they do so without any awareness that a species 124 light-years away has begun to wonder about them. This is the strange intimacy of astronomical observation, the way we can study a world in such detail while remaining utterly separated from it by distances that mock our fastest technologies. We know the composition of its atmosphere, the size of its orbit, the mass of its parent star, yet we cannot say with certainty whether anything lives there waiting to be discovered. The ocean world keeps its deepest secrets, revealing only what physics and chemistry require it to share through the light it cannot help but emit and reflect. Perhaps someday, generations from now, humanity will develop technologies that make such distances less forbidding, less absolute in their separation of worlds from one another. Perhaps our descendants will find ways to send probes across interstellar space, patient machines that travel for centuries to finally arrive at worlds like K2-18b and report back what they find. Or perhaps we will remain forever bound to our own solar system, learning about the universe only through the light that comes to us across the patient darkness. Either way, the wondering is worthwhile, the questions valuable even when answers remain beyond our grasp for now or perhaps forever. To look up at the night sky and know that ocean worlds exist out there, wrapped in hydrogen atmospheres and orbiting ancient red stars, is itself a kind of gift. Our generation is the first in human history to possess this knowledge, the first to understand that the cosmos is filled with worlds stranger and more beautiful than our ancestors could have imagined in their most vivid dreams. K2-18b is 124 light-years away, a distance we cannot cross, orbiting a star we cannot see without technological assistance that our ancestors could never have conceived. Yet tonight, in some meaningful way, that world exists in your mind as well as in the constellation Leo, a place you have explored through words and wonder and imagination. You have traveled there in the only way currently possible, carried by knowledge rather than spacecraft, and you have glimpsed what science has revealed about its alien seas. The ocean world will still be there tomorrow and the day after, and for billions of years beyond any timescale that matters to human concerns or individual lives. Its star will shine long after our sun has exhausted its fuel, providing warmth to whatever floats or swims or drifts in those global waters beneath hydrogen skies. Time moves differently at cosmic scales, patient and unhurried, and worlds like K2-18b have more of it than we can properly comprehend or fully appreciate. The universe is vast and ancient, filled with wonders that we have only begun to catalogue, let alone understand in any depth that approaches completeness. Every observation opens new questions. Every discovery reveals how much more remains hidden beyond the current reach of our instruments and our understanding. This is not frustrating but exhilarating, a reminder that curiosity will never run out of territory to explore. The wonder will always find new objects worthy of its attention. Tonight, you have explored one small corner of this vast cosmic landscape. One ocean world among billions. One story among countless stories waiting to be told in the fullness of time. The facts you have encountered will settle into memory, and some will stay with you while others drift away like clouds across a twilight sky on a distant alien world. What matters is not perfect retention, but the experience of wondering, the gentle expansion of imagination that comes from considering possibilities beyond our immediate, everyday experience. The stars outside your window, if you can see them, are the same stars that astronomers study with sophisticated instruments worth billions of dollars and representing decades of engineering progress. You share the same sky with the largest telescopes on Earth, looking up at the same ancient light that has traveled for years or centuries to reach this one small blue planet. In that sense, we are all astronomers tonight, all participants in the human tradition of looking upward and asking what might be out there, waiting for us to discover it. K2-18b orbits on, indifferent to our observation, unconcerned with the papers published about its atmosphere or the speculation about what might swim in its seas. The planet exists as it has for billions of years, following the path that gravity and momentum set for it, long before Earth even formed from the dust around our young sun. Our attention changes nothing about that distant world, adds nothing to its oceans, subtracts nothing from its skies that stretch perpetually overhead. But our attention changes us, expands our sense of what the universe contains, deepens our appreciation for the strange and beautiful diversity of worlds that orbit distant stars across the galaxy. We are slightly different for having contemplated this ocean world, slightly larger in imagination, slightly more aware of the possibilities that exist beyond the horizon of our own small planetary experience. This is the gift that astronomy offers, not practical knowledge, but expanded perspective, a reminder of context that can make our daily concerns feel appropriately small. The night continues, and you have traveled far. Tonight, 124 light years to an ocean world that may harbor secrets we will not uncover for generations yet to come. The journey required no spacecraft, no decades of travel, only attention and imagination, and the willingness to follow where knowledge leads across the cosmic dark. You have been, in your own way, an explorer tonight, visiting places that exist beyond the reach of any technology we currently possess. Rest now if you are ready, letting the thoughts of distant oceans and hydrogen skies settle like sediment drifting slowly to the floor of a calm and ancient sea. The universe will continue its slow operations while you sleep. Stars fusing hydrogen into helium, planets spinning through their orbits, light traveling across the darkness toward destinations it will reach long after tonight has passed into memory. Nothing requires your attention now. The cosmos will keep its own time without any need for human witness. K2-18b will complete another fraction of its 33-day orbit before you wake, moving just slightly further along the path it has followed for billions of years around its dim red star. The ocean that may cover its surface will continue doing whatever oceans do on such a world, unmeasured and unobserved until the next telescope turns its way to gather more ancient light. And somewhere in the constellation Leo, too faint for human eyes but not for human curiosity, that small red star will keep on shining as it has for billions of years. The story we have shared tonight is part of a larger story that humanity is slowly learning to tell. The story of a universe filled with worlds beyond counting and wonders beyond imagining in their full scope. You have heard one chapter of that story, and there are more waiting whenever you wish to return to this channel and explore more of the cosmos that surrounds us. For now, let the thoughts grow quiet, let the distances grow soft, let the wonder settle into the peaceful rest that follows a journey well taken. The stars will keep their vigil while you sleep, light traveling across distances too vast to truly comprehend, carrying information about worlds we may never visit but can always imagine. Tomorrow the universe will still be there, ancient and patient and full of mysteries that will take humanity centuries more to unravel and perhaps never completely solve. But that is a gift, not a burden, a promise that curiosity will always have somewhere to go and something to find. Good night from the drowsy astronaut. Sleep well, and we'll explore the cosmos together again soon.